Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about JWST, James Webb Space Telescope's first images. Now, these are images that are finally sent for scientists to actually analyze. These are not calibration images, not test images, not trial run. This is like final, okay? Science mission has started. That's what we are talking about here. So this is Carina Nebula. Now, why this section is interesting? Because it shows something very interesting. First, this is very young area, meaning it's active, quote unquote, and it's star formation region, meaning this is technically classified as star nursery, meaning new stars are born in this sort of locations. And technical code is NGC3324. Who knows? Now, this boundary wall is kind of interesting. Now, it's like, what could cause such a boundary in space? Like, this is multi-light year, kind of equipment, and like this spot could be around 7 light years. So, what's causing this sort of galactic level stuff? Well, it's if you have seen the anime Naruto, so this is its galactic version of Almighty Push. So who is doing the pushing here? Well, it's the young stars that are ludicrously bright in ultraviolet, meaning they are pushing insane amount of radiation. The radiation pressure is so much, it's almost acting as like sweeping net, meaning we know for a fact that our sun has a zone where dust cannot enter simply because radiation pressure will push it away. Unless it's like a big boulder, then it will crash and melt, but like dust cannot be there without, within a specific sphere. Here, because these stars are so young and so powerful, they're like just pushing it. Now, what's happening with that? Well, this is creating this interesting pattern, and on top of that, these places will collapse over time, and they will start to birth their own stars. And one other interesting part, we wanted to use what we call as infrared. Now, why we wanted to use infrared? Somebody will say, Doppler shift. That's also true. Now, there is another interesting aspect, especially with dust cloud. The longer your wavelength goes, the more through things you can go. For example, radio waves, it can go through things, it can go travel very long distance, but the moment you increase your frequency, it does not do that. Like, be it your Wi-Fi, like if it's 5 gigahertz, it does not go far. 2.5 JJ. Now, same goes with all spectrum, meaning the longer the frequency, the longer the travel distance you're gonna get. Here, Hubble took this photo, and other observatories took the photo. They were seeing some stars. Basically, any star that you can see the cross pattern is super bright from its point of view, and that's a very good indication of its basically distance from you. So, but there are many other small dots here. Now, that dots were not visible. Why? Because they were hidden behind the dust cloud. Because of Hubble's limitation with optical spectrum, they could not do much. This very low infrared system, it can just pass through. The radiation can just simply pass through the dust cloud. It's like, it does not care. So you can see these things. These are very low faint stars. Again, bright stars we can see simply because the lenses are so huge. But small ones, faint ones, that requires observation time and sensitivity. We have the sensitivity in infrared spectrum. That's why we can see through this part also. Because if you see older images, you will always find like this part, we can see clearly. This part, not so much. Only some stars are here. It almost look like this is a soil wall here. But that's not the case. And that's the proving ground, so to say. That's like, now study this far more clearly and today. Then we come to another nebula, Southern Ring Nebula. Now, this nebula is kind of interesting because this is a death of a star, so to say. Now, this happened kind of close to us, 2,500 light years. Again, from a galactic point of view, that's super close. And one of the interesting things is, like, if you watch all the photos of this puppy before this puppy, you will find that everybody's talking like this is a single star. Like, maybe some observatories have figured it out, like it may not be a single star, but there was no clear photo. First time we can see, hey, wait a minute, there is another small star here. That's the whole point of sensitivity. Different sensitivity in different spectrum allows you to see through things. We could see this same thing, same location, exact same thing. Again, these two are same things and only shifted little bit in electromagnetic spectrum. Now imagine what you will see if you are using ultraviolet. That's why we also build ultraviolet observatory. Same thing will happen if you use X-ray. That's why we build X-ray observatories. That's the whole reason why science tries to focus on whole of electromagnetic spectrum. Ideally, you will have something that can focus on like very large chunk of it. Basically, it may start as like very low, for example, very low infrared, and go to very high, like high infrared or like light X-rays, so to say. Then you can see very like serious amount of things. But this, right now, we don't have that technology, so we make different observatories and different instruments to sense that, observe it properly. And you can see that, like, 1 star, 2 star, what the hell happened? Dust cloud. So this is another interesting thing. Now, what is this material? This is the material then stars are the forge of this world, basically. Because if you look at Big Bang, all our mathematics suggests there is only light elements there. What light elements? Majority hydrogen. So how the hell entire periodic table came to be? Something's triggered it. What triggered it? Fusion. Basically, you take hydrogen, fuse it into helium. You do the same thing in the entirety of periodic table until you reach iron. The moment you reach iron, you had a paradox. Basically, iron will not give you energy. It's like, no, I will not give you energy. So consequences, when stars tries to fuse it, it absorbs energy. And the gravitational pressure is like, now I win. It's almost like, how a plane can stay afloat as long as it has fuel. Same thing is with the star. Star can stay star as long as there is fuel pushing outwards. Basically, reactional energy is pushing it outwards. When not there, now what happens there? That depends on the starting mass. It can be blown away like this, or it can be like collapse into a black hole. Generally, it will be blown away. But very few stars are that huge. So this happens like blowing away. Now, what is here? This is the interesting part. This sort of nova kind of structure generally creates everything heavier than iron. Now, these are pulse creation, like hydrogen to helium is a constant conversion. But this happens on that first time the star goes boom, that happens. So then you can go as high as like, uranium. So whenever somebody says like, where's the energy from your nuclear reactor is coming from? It's not coming from sun. It's coming from other suns that have died, created nova, that created the conditions, like, bow shock sort of conditions. In this sort of condition, you will find heavier elements. And you may even find whole complete compounds. For example, hydrocarbons can be found here. So that's another part of the interesting details. Because of the spectrum graph that we are getting out of it, it's so detailed, we are like, no, we are not just saying there are things here. We are saying, no, this compound is here. That's why it's so interesting. So ejecting material, and this material will be slowly fading away throughout the galaxy, and then will be absorbed by other stars, other dust clouds, and then it will become either another star or another planet like us. So that's why this one is interesting. Then we come to SMACS. SMACS 0723. Now this part is very interesting simply because Hubble also took it. And to give you a context of size, how small area we are looking, take a grain of sand and just like do like this. That's how small area you are looking at. It's like insanely tiny. And I'm reasonably sure if you do the maths, grain of sand might be bigger. So it's very small. Now, what's so interesting here? Interesting part is here is like before Hubble did this, we had a sort of understanding that we understand the distribution of galaxy. We kind of, have a handle on things, how many galaxies are there. Now, this experiment that was done just to like, just for lols, focus on this place. Now, again, it was not for lol, but you get that point. Like people are like, why are you looking at a place where we know there is nothing there? It's just like this place, we know nothing is there. Okay, now focus on that place. Take a very long exposure, very long exposure. Now, after doing that, there were like whole galaxies. Everything you are seeing splotches here, they are galaxies. Now, here's the other interesting part. If you're seeing things that have spikes, these are very close stars. Because of the light diffraction, it has that spike. Now, why it has this spike? Because of the hexagonal mirror system. That's why Giant Magellan Telescope still uses a round surface. You do not want the spikes in Giant Magellan outcomes. And not to mention then why there's this extra cross, it's coming from the two arms that are there. Now they tried their best to like hide the arms into the diffraction pattern, and they successfully did that. That's why there is not 8 cross section. They aligned it. That's why 2 arms that are on the bottom end of the support mirror, it's like this. It's specifically aligned so that its frequency matches and closes. Like it's just one diffraction. And then we come to the our top one that can't be done anything about it. So it's like this line. That's why if everything would have been done perfectly, we would have only 6 spikes. So right now we have that like 7 spike. That's because of that. Secondary mirror, it has the third line. Again, due to weight constraint, even if they wanted to add the same angled system, it would have added too much weight. So pros and cons. So anything that is like this bright, anything that has like spikes, they are generally very close to us. Anything that is very blobby, generally it's a very far away object. So you can see very clear gravitational lensing, meaning there are these puppies and they're bending the space-time around it. And you can see it like how much they are bending. And this bending is very interesting simply because it allows you to calculate the mass of this puppy. It's very interesting. It's like we thought like this place has nothing. Hubble is like, let me show you. Now this puppy is, let me really show you. And I'm hopeful that when we have even larger brothers of this, they're like, then we'll focus on this tiny patch and it's like, 10,000 galaxies here. So that's the interesting part of this image. It's like A, gravitational lensing is super clear. B, is like how many things we are seeing. And it's like, wow. This is like they took a Hubble deep space and it's like, let me show you. Then we come to Stephan's Quintet. I'm very sorry about names. Now this puppy. Now what is happening? Basically, it's a lot of galaxies getting married together. And interesting part, all these small dots that you are seeing, they are actual stars. And that's the reason of having huge mirror. The bigger the mirror, the more clearly you can resolve this. Every other observatory will just give you splotches here. And not to mention other Earth observatory will have an issue where they have to try to correct for Earth's atmosphere distortion. They can get down to very small, resolving resolution resolution, but this much is very difficult to achieve. So that's amazing. Like this, all that's dot, they are actual stars. That's like mind-blowing. Like it looks like ISO noise. It's not noise. It's like goddamn dots. So this galaxy is kind of close to us. It's around 290 million. Given the fact that every other photo that we are talking about is in like, billions of years, this is super close. And this happens when galaxies crash into each other. Now, many times you may have had this question. It's like, how the heck astronomers know things? It's like, we have only one star. How the heck we know star goes through, this phase? That's the whole point of astronomy, because you are studying it. Think of it this way. You are in a forest, and let's say you are next to a tree. Is that tree, exact same age as every other tree? Hell no, that's not going to happen. You're going to have some trees that are very young, that are growing. You will have some trees that are very old and decaying. There are some trees that are already dead. So that's why studying the forest, you can figure out what is the life cycle of a tree. Same thing we are doing here. We are studying our own galaxy to best of our ability, but problem is the same thing. And it's like in same time frame. Now, if you are observing, you will find other galaxies that are a bit younger and bit older. You are seeing other galaxies that are crashed into each other, meaning many times you would have also heard that we are saying that Milky Way is going to collapse with Andromeda galaxies. Like, how the heck you know this is going to happen? Because we have seen it. We have photographs of other two galaxies going bang. Same thing is happening here. There are other galaxies that have gone through each other and they have like, distorted in shape. We have seen things that are like, coming close to each other. So taking this, all the snapshots, we figured it out. Like if your trajectory is like this, most likely you're going to crash. So same thing is happening here. Studying this figures out allows us to understand what actually happens when galaxies goes through each other. Now, be mindful is generally going through each other, only being affected by gravity, because the probability of stars, planet, moons actually colliding with other star, planet, moons is very minuscule, simply because the gap between each of these two dots could be tens of light year. So basically they are mostly empty space going through each other. So that's the interesting part of it. And you can even see a huge bow shock that is being created here. All these things are very interesting. Think of it this way. When we sent Voyager, and we said like, Voyager has crossed a bow shock of sun. Again, it's not visible to us, but if you take a basically telescope, you went it like hundreds of light year away, and you're taking long exposure of sun, you will find there is like, a gray area, which we have just crossed with our Voyager probe. That's the whole point. Same thing is happening here. Basically, people who are living in here, they will not notice it. They're like, same way we are looking at basically, Andromeda galaxy. It's like, oh, that galaxy is a bit too close. That's the whole point. And again, even we could have disturbance. We could have a scenario where you have a civilization, but like because their draw of the luck was so bad that like they crossed way too close to other star or planet, and their orbits got disturbed. That could happen. That's like, again, these things are not, mostly they are empty space going through empty space, but there are some gravitational disturbances if you have bad day. Now, how this photo was taken, because this is a very large patch of sky. To give you a context, this sort of patch of sky we are talking about. Now, again, this is the final target that James Webb will do. Right now, it has not done this. And all the red dots you are seeing, they are from near camera, and everything blue you are seeing is from near camera. Now, the idea with this puppy is that it's going to take a giant collage to study this thing. So this sort of system is done when you want to study large objects, because again, your field of view is kind of focused. It's not a zoom lens, it's a prime focal lens. So you can't do much in terms of, basically, you can focus near or far, but you can't change the field of view. So in those sort of scenarios, this sort of system is used, basically multiple exposure. And this, like, if you're like, wait, I can't see any borders, amazing engineering. So this is the quintillion basically, and one of them is like very far apart. It looks close to each other, but this puppy is much farther apart. And again, same spikes, they are close to us. So what's the point of all this sort of system? And again, I did not talk about the graph because it's a graph. It's not a graph image. So money cannot buy time. This is one amazing quote from Endgame. It's like, no amount of money ever bought a single second of time. That's absolutely true. However, money can buy you speed. Now, speed is another critical aspect. Think of it this way. Let's say you wasted your early years and then you became super rich, and now you're doing things much quicker. Now you become even hyper rich. Now you're doing even quicker. Now you are ludicrously, it's like so rich that you are like, even if your wife takes 50% away from you, you're like, I'm still the richest man on this planet. Damn. So in those terms, you understand the value of speed. So all these observatories, they are focusing on speed, meaning, can Hubble give you something similar to this? Yes, it's just exposure would be idiotically long, meaning it will be like, yeah, just focus on this region for like a year. And not to mention, Hubble is in low Earth orbit, so it has a consequence that unless things are focused directly on pole and pole, it has to go through like, Earth's shadow, meaning Earth will act as a occlusion body. So it has to focus on something else when it's going through the shadow. So that creates a limitation on how long exposure it can do. On some areas, it can't do really long. But James Webb was like thought about this. It's like, can we do something better? Yes. That's why it was put in Lagrange point. So that's the whole. The great advantage of its location is uninterrupted exposure, meaning it can focus on one area and just give one ludicrously long exposure. It could be as long as few months. That's the whole interesting aspect of it. That's why that specific location was chosen. It's like very large sky, portion of sky is like completely exposed to us. Like we don't even have to think about it. It's like you want to focus on that area, focus on there. It's not like, okay, where the earth will be, where the moon will be, what will be the occlusion. No. Just you want to focus there, focus there. That's the interesting aspect of here. And it can do large observation quickly, meaning this deep spin, this puppy was done in days. This was done in hours. Let that sink in, days and hours. That's the whole point, meaning we will see amazingly large amount of things if we are focusing on, like, places that are like dark patches, truly dark patches, and we are like, James Webb, go for 11 days. It like I'm actually would be surprised if it's not overexposed. So that's the whole point. You want to do things quickly as possible, like as quickly as possible. This whole exposure, you can see things. That's good, but again, that's the aspect of spectrum you are using. Like if you use X-ray, you will see different things here. You use microwave, you will see different things. You will use radio wave, long radio waves, you will see different things. You will use infrared, you will see different things. That's why we have different sort of observatories. But having it large, having it expensive allows you to do it quickly as possible. So we can see really far back, and we can see patterns, basically how galaxies are forming. We can see that when the example of forest applies here. Basically, if we can see almost to the Big Bang, we can see how early galaxies were formed, and that requires a huge surface area. That requires a uninterrupted view of one place where you can just like, I'm going to focus on this puppy for, let's say, 6 months. That's why we are like, so focused on this basically. And another benefit of seeing through dust cloud is just the spectrum is like, you yoinked it. And you may be like, wait a minute, I'm talking about infrared. Why the heck these are color images? It's basically you're shifting it. You're taking the infrared, taking it out, and sliding the whole mathematics with complete detail into infrared. It's like it's also done in radio technology, meaning for many amateur satellite enthusiasts like me, we can't actually afford high frequency radio receivers that are used for like, modern satellite. I'm using like older satellites like NOAA satellites and Meteor Russian satellites. They're old satellites. Newer satellites use very high frequency. Problem is the receiver, SDR for newer high frequency, they are expensive. So people do a downshifter, meaning it will take something like, let's say, 5 gigahertz and it will downshift it to 2 gigahertz. It's like, wait a minute, that can be done? Yeah, it can be done. Same thing is happening here. You can shift whole data. You can take Control C and Control V into different patch and get same resolution. And not to mention, if you're talking about something that has been red shifted, inherently that's what happened to it. You're just blue shifting it again. So it's not fake, it's not created, it's not painted, it's just shifted, because otherwise you will not see it, and you will need a monitor that can show infrared. Good luck with that. So, and again, what would be the point? We will still be like, it will look like a warm heater to us. So that's the reason. That's why we are doing what we are doing. We are buying speed. Now, we can't buy time, so we are buying the next best thing, speed. So this was my presentation on basically newly released images. That's why I did not talk about a spectrum. Newly released images of James Webb Space Telescope. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.